So in this video, we're going to talk about the existence of derivatives. They won't always exist. All right, so the thing to remember is the definition of the derivative, or the kind of formula we're using, involves a limit. And we saw a lot of different times when we were talking about limits in the first 2 units that there's a lot of times where limits don't exist. So since limits don't exist, sometimes the derivative doesn't exist. Okay. So there's one nice case. We talked about continuity for an entire unit. All right, if f of x is differentiable, so that just means if the derivative exists at a, then it's also continuous. All right, so if we're able to take a derivative, then our function has to be continuous. All right, that's not super useful for us because we're asking, well, when doesn't the limit exist? This assumes the derivative does exist. But there's something in math called the contrapositive, so this also means that if f is not continuous, f cannot be differentiable. All right, so this is one of the reasons we talked about continuity for a while, because if our function is not continuous, then it's also not possible to take the derivative. All right, so that's one of the reasons when you won't be able to take a derivative if your function is not continuous. Remember, some of those reasons were removable discontinuities that might look like that. There could be jump discontinuities. There could be asymptotes, infinite discontinuities. So all of these things are not going to have derivatives at those points where it's not continuous. It'll have derivatives at other points, but not where it's not continuous. All right, and there's a couple other cases. So that's the kind of straightforward one. If your function is not continuous, then you can't take the derivative. But there are continuous functions that also don't have a derivative. All right, this is one case, the absolute value of x. Let's just graph the absolute value of x. It looks like a v. And pretty much everywhere around here, the derivative is going to exist, but the one problem is going to be right here at 0. And it's important to remember that our derivative is a limit, and it's the limit of kind of the average rates of change around there. And if we look at the average rate of change on the left, they're all going to be going down this way. All right, so for every single average rate of change, if we're using a point on the left, we're going to get -1 as our average rate of change, which would mean that the derivative should be -1, right? Because we just use the average rate of changes to approximate the derivative. If we're going to use any point on the right of 0, well, now all of my changes are going up to the right. I'm going up to the right. That slope is +1. And if they're all +1, it makes it look like the tangent line should also have a slope of 1, because they're all 1. Well, if I use any number on the left, it looks like it should be -1. Any number on the right, it looks like it should be +1. And those two things don't agree. They don't level off. So there's kind of a jump in the tangent lines, in the approximating secant lines. So there's no tangent line that makes sense. Like this, the left-hand side says the tangent line should look like that. The right-hand side says the tangent line should look like that. And again, in math, when there's two things that don't agree like that, we're just going to say it does not exist. So in general, anytime you have a sharp corner in your graph, all right, the derivative is not going to exist because the tangent lines are going to kind of be competing. So any sharp corner in your graph, and sometimes they're called cusps, any of those are not going to, the derivative is not going to exist. It is continuous, but the derivative doesn't exist there. At another time, the derivative won't exist is if we look at the graph of the cube root of x. Looks something like this. And again, let's look at x equals 0. What's going to happen here? Well, everything looks fine. There's no sharp corners, there's no cups. It is continuous because I just drew a solid line. But I think about the tangent line. As I turn from the bottom to the top, my tangent line would kind of level off in the middle there. And this red line would be my tangent line. Well, what's the slope of this? All right, the slope of this, the rise, let's just say I pick these 2 points. The rise would be something like 2. The run, I don't go left or right at all, so the run is 0. All right, again, that's bad. I'm dividing by 0. All right, so anytime I get a tangent line that's going straight up and down, which is called a vertical tangent line, the slope of that vertical tangent line does not exist, which means the derivative, which is just the slope of the tangent line, also can't exist. All right, so that's another reason when the derivative will not exist when you have a vertical tangent line. All right, so those are kind of our main reasons when we're talking about derivatives existing. If it's not continuous, the derivative doesn't exist. If there's a cusp, the derivative doesn't exist. And if you have a vertical tangent line, the limit doesn't exist. Or sorry, the derivative doesn't exist. All right, but what about these types of functions? All right, again, piecewise functions are always weird things because you're switching between them. What about this piecewise function? Is it going to be differentiable at 2? And again, 2 is important because that's where the switch is happening. If we were asked about continuity, we would just plug in 2 into each of these. We get 7. So this function is continuous. But again, just knowing continuity is not enough to declare that it's also differentiable. Our differentiable is an extra thing on top of continuity. Right. It is possible. Right. What do we know? We looked at this in class. Before 2, my function is just this line 3. And if you have a line, the average rate of change is the same as the instant rate of change. It's just the slope of that line. So to the left of 2, my average rate of change is 3. To the right of 2, it's a line again, so I'm just going to go a slope. The average rate of change is 5. And those don't agree, so everywhere to the left of 2, my function would be slope 3. Everywhere to the right of 2, my function would be slope 5, which is steeper. And you can see it creates this corner right there that would be bad. So even though it is continuous, it is not differentiable at 2 because the slopes of these incoming pieces do not match up. All right, what about this function? Is the following function differentiable at 2? Again, 2 is where the change happens. The top function, again, is the same. The tangent line is just going to have the same slope as the line, which is 4. So to the right of 2, my derivative is 4. To the right of 2, I'd have to figure out what is the derivative of x squared at 2. This is actually a problem that we did before. All right, the derivative of, that doesn't make sense what I'm writing. But if you find the derivative of x squared at 2, you're also going to get 4. All right, so right at 2, the derivatives of these functions are going to align, which means it's going to be a nice smooth thing. So to the left of 2, I have my line. To the right of 2, I have my x squared graph. But you can see it kind of smoothly turns from a line and then into the curve. There's no sharp corner there. This one actually is differentiable. So it is continuous, and because right at 4, they're kind of both going in the exact same direction, it is differentiable. All right, so do a little more practice with this in class as well. But again, always with piecewise functions, we have to check what happens when we change from one rule to the next.